Next topic is spatial convolution and correlation. Before moving into convolution and correlation, we will first see what is spatial filtering. Filtering refers to accepting or rejecting certain frequency components, and this effectively smoothens or sharpens the image. Uh, we use different low pass filters or high pass filters, etc., to filter the images so that it is more smoothened or sharpened, etc. Okay, so if this operation performed on the image pixels is linear, then the filter is called a linear spatial filter. Otherwise, it is called a non-linear filter. Okay, so filtering is simply accepting or rejecting certain frequency components. Okay, so what is correlation and uh, convolution? These are actually linear spatial filtering techniques. So this correlation and convolution both are very closely related concepts. Both are used to extract information from images, and both are basically linear and shift invariant operations. Okay, what do you mean by shift invariant? Shift invariant means that the same operations are performed at every point in the image. That is, when you are applying a filter on the image, it is applied on every point or every pixel in an image. Okay, so that is called shift variant invariant. Okay, and the term linear means that the pixel is replaced by linear combination of its neighbors. Okay, so we use some linear equations to replace the pixels. So that is why it is called linear operation. Okay, so correlation and convolution are basically linear and shift invariant operations, and they are used to extract some information from images. That is, it's some kind of linear spatial filtering techniques. Okay, so what is correlation? Correlation is a process of moving a filter mask over an image and computing the sum of products at each location. Okay, so say you will have a, when you apply a filter on an image, moving this filter mask over an image and computing the sum of products at each location, that is called as correlation. And convolution has the mechanics are same in case of convolution, except that the filter is first rotated by 180 degrees. Okay, so here we are going to see only in detail about spatial convolution, since we have already seen how this edge detection is performed by convolving the mask onto the image. Okay, so how this spatial convolutions are done, that's what we are going to see again. Okay, in spatial convolution, here it replaces a pixel with the weighted average of the pixel and its neighbors of the convolution mask. Okay, so it simply replace a pixel with the weighted average of the pixel and its neighbors of the convolution mask. Okay, so convolution is basically a mathematical operation where each value in the output is expressed as a sum of values in the input multiplied by set of weighting coefficients. Okay, so that is shown here in this equation. Okay, in this equation you can see it is the sum of values in the input multiplied by a set of weighting coefficients. Okay, so this weighting coefficients will be from the mass. An image can be either smoothened or sharpened by convolving the image with respect to low pass and high pass filters, respectively. So, an image can either be smoothened or sharpened using this uh, convolving of mass, that is high pass or low pass filters with this with the image. You can either smoothen or sharpen the image. Okay, and it is used in application including image filtering, image segmentation, feature extraction, etc. So here, two-dimensional discrete convolution between two signals x n1 n2 and h n1 n2 is given here. Okay, so uh, that is spatial convolution. If you do a problem, you will get a better idea about it. So we will do a problem on it. So this is our problem. You have to perform linear convolution between two matrices xn1 n2 and hn1 n2. xn1 n2 is 1 2 3 4, this 2 by 2 matrix, and hn1 to n1 n2 is a um, 3 4, which is a matrix with one row. Okay, so this can be represented as an image like this. So you have, this is n1 and this is n2. So in x1 and xn1 n2, this is 0 0 location, this is 0 1, this is 1 0, and this is 1 1. So this can be represented as 0 0 is here, 1 0 1 is this location, so that is 2, then 1 0 is this, so that is 3, and 1 1 is this, that is 4. Okay, so this is represented like this, and similarly h n1 n2, this matrix can be represented like this, n1 n2. So this is 0 0 location and this is 0 1 location, so this is 3 and 0 1 is 4. Okay, so this is the representation of this matrices. Okay, so what you have to do is you have to find the linear you have to perform the linear convolution between these two matrices, and we know the equation y n1 n2, where y n1 n2 is the resultant matrix, resultant convoluted matrix, that is equal to x n1 n2 star h n1 n2. Okay, so this is equal to sigma minus infinity to infinity, k1 equal to minus infinity to infinity, sigma k2 equal to minus infinity to infinity, x k1 k2 into h n1 minus k1 comma n2 minus k2. Okay, so this is our equation. So the resultant matrix had y, this is for each location in the matrix y, you have to find the convolution between x and h. Okay, so uh, uh, the dimension of the resultant matrix y is of resultant matrix um, is equal to number of rows in x n1 n2 plus number of rows in h n1 n2 minus 1 by number of columns in x n1 n2 plus number of columns in h n1 n2 minus 1. Okay, so here resultant matrix y n1 n2, the dimension of y n1 n2 will be equal to 2 plus number of rows in x n1 n2 is 2 plus number of rows in h n1 n2 is 1 minus 1 by number of columns is x n1 n2 is 2 plus number of columns in h n1 n2 is 2 minus 1. So that is 2 by 3. So there should be 2 rows and 3 columns in the resultant matrix y, dimension of y. Okay, so this is our dimension for y. So the resultant matrix y will be something like this: y 0 0, y 0 1, y 0 2, y 1 0, y 1 1, y 1 2. So you have to find the value for each location in this matrix. Okay, so first you have to find y 0 0. Okay, so here n1 is equal to 0 and n2 is equal to 0. Okay, so for n1 equal to 0, n2 is equal to 0, you have to find, what you have to find is y 0 0 is equal to x 0 0 star star h n1 n2. Okay, it's 0 0. So you have to find the folded n2 h n1 n2. Okay, so you have to first find the folded version of h. Okay, so initially h is represented like this: n1 n2 3 4. Okay, so after performing to find folded version of h k1 k2 is equal to h n1 minus k1 n2 minus k2. That is, you have to find for h 0 0 will be h 0 minus 0 comma 0 minus 0, that is equal to h 0 0 itself, and h 0 1 will become h 0 minus 0 and h 0 minus 1, that is equal to h 0 minus 1. So our new h will be, so in the new folded h will be like this. Okay, this is h 0 0 will become h 0 0 itself, so this is 3 and h 0 1 will become h 0 minus 1, so the location will be here. So 3 4, so this is 0 0 and this is 0 minus 1. Okay, so by convolution, of these two matrices, that is x n1 and 2, that x n1 and 2 is 1 1 2 3 4, convolution with the matrix, folded matrix H will be this 3 4. Okay, this is 0 0 0 minus 1. Okay, so this will be taking common terms, in both. Weighted sum will be equal to, that is our y0 0. That is, here common term will be only this and this. Okay, so 3 into 1, that is equal to 3. So our y0 0 is equal to 3. Okay. Similarly, you have to find all the other 5 locations. So now next to find y0 1, n1 is equal to 0, n2 is equal to 1. So you have to find the folded edge. So h0 0 is equal to h0 minus 0, comma 1 minus 0. So minus 0, that is, here n1 is 0, n2 is 1, and k1 0, k2 0. So it will become 0 1. Only h0 1 becomes h0 minus 0 and 1 minus 1, that is equal to h0 0. Okay, so folded h n1 and 2 will be h0 0 become h0 1 and h0 1 become h0 0. So you have to perform convolution between the matrix like this. So this is our matrix 1 x. This is our x star star, our folded edge. So the folded edge will have h0 0 becomes h0 1. So this is 3, and h0 1 becomes h0, so it will be 4. Okay, so this is our folded edge. Okay, and by convolution, so you have to find the weighted sum of the common terms. So weighted sum of common terms, here common terms is 1 4. So y0 1 is equal to 1 into 4 plus 3 into 2, that is equal to 4 plus 6, that is equal to 10. So y0 1 is equal to 10. Okay, then next is y0 2. So to find y0 2, here n1 equal to 0, n2 is equal to 2. So folded edge can be found by h0 0 will become h0 minus 0, it's 2 minus 0, so that is equal to h0 2, and h0 1 will become, folded edge will become h0 minus 0, h2 minus 1, that is equal to h0 0, 1. Okay, 0, 1. So by convolution, by performing convolution of x and folded edge, this is 1, 2, 3, 4. Performing convolution with a folded edge. It is here x0, 0. 3 will be at the location x0, 2. So it should be somewhere here. So this is 3 and x0, 1 is 4. Okay, so here common location is this term and this term also. Our y 0, 2 is equal to 4 into 2, that's equal to 8. Okay. Similarly, you have to find for y10, y11. So for y10 is equal to 9, for y11 it's equal to 24. Similarly for y12 it's 16. So our final matrix, final convoluted matrix is y n1 n2 y n1 n2 is 3, 10, 8, 9, 24, 16. Okay, so this can be represented like this: 0, 0, 3, 0, 1, 10, 0, 2, 8, 1, 0, 9, 1, 1, 24, and 1, 2, 60. So this is our image after convolution. Okay, so this is spatial convolution technique.